The year 2000 problem was a problem for both digital and non-digital documentation and data storage situations that resulted from the practice of truncating a 4-digit year to 2 digits. This made year 2000 indistinguishable from 1900. The former assumption that a 20th century date was always understood caused various errors concerning, in particular, the display of dates and the automated ordering of dated records or real-time events. In 1997, the British Standards Institute developed a standard, DISC PD 2000-1, which defines year 2000 conformity requirements as 4 rules. No valid date will cause any interruption in operations. Calculation of durations between, or the sequence of pairs of dates will be correct whether any dates are in different centuries. In all interfaces and in all storage, the century must be unambiguous, either specified, or calculable by algorithm. Year 2000 must be recognized as a leap year. It identifies 2 problems that may exist in many computer programs. Firstly, the practice of representing the year with 2 digits becomes problematic with logical error arising upon rollover from X99 to X00. This has caused some date-related processing to operate incorrectly for dates and times on and after the 1st of January 2000, and on other critical dates which were build event horizons. Without corrective action, long working systems would break down when the 97, 98, 99, 00 ascending numbering assumption suddenly became invalid. Secondly, some programmers had misunderstood the Gregorian rule that determines whether years that are exactly divisible by 100 are not leap years, and assumed the year 2000 would not be a leap year. Although 3 out of 4 years divisible by 100 are not leap years, if they are divisible by 400 then they are. Thus the year 2000 was a leap year. Companies and organizations worldwide checked, fixed, and upgraded their computer systems. The number of computer failures that occurred when the clocks rolled over into 2000 in spite of remedial work is not known. Among other reasons is the reluctance of organizations to report problems. Background: Y2K is a numeronym and was the common abbreviation for the year 2000 software problem. The abbreviation combines the letter Y for year and K for the SI unit prefix kilo, meaning 1000, hence, 2K signifies 2000. It was also named the Millennium Bug because it was associated with the popular rollover of the millennium, even though the problem could have occurred at the end of any ordinary century. The year 2000 problem was the subject of the early book Computers in Crisis by Jerome and Marilyn Murray. The first recorded mention of the year 2000 problem on a Usenet newsgroup occurred Friday, 18 January 1985, by Usenet poster Spencer Bollis. The acronym Y2K has been attributed to David Eddy, a Massachusetts programmer, in an email sent on 12 June 1995. He later said, "People were calling it CDC, FADL, and other names. The problem started because on both mainframe computers and later personal computers, storage was expensive, in many cases as much as or even more than $1 per byte. It was therefore very important for programmers to reduce usage. Since programs could simply prefix 19 to the year of a date, most programs internally used, or stored on disk or tape, data files where the date format was 6 digits, in the form MMDDYY, MM as 2 digits for the month, DD as 2 digits for the day, and YY as 2 digits for the year. As space on disk and tape was also expensive, this also saved money by reducing the size of stored data files in databases. Many computer programs stored years with only 2 decimal digits. For example, 1980 was stored as 80. Some such programs could not distinguish between the year 2000 and the year 1900. Other programs tried to represent the year 2000 as 19,100. This could cause a complete failure and cause date comparisons to produce incorrect results. Some embedded systems, making use of similar date logic, were expected to fail and cause utilities and other crucial infrastructure to fail. Some warnings of what would happen if nothing was done were particularly dire. The Y2K problem is the electronic equivalent of the El Niño, and there will be nasty surprises around the globe. John Hamra, United States Deputy Secretary of Defense. Special committees were set up by governments to monitor remedial work and contingency planning, particularly by crucial infrastructures such as telecommunications, utilities and the like, to ensure that the most critical services had fixed their own problems and were prepared for problems with others. While some commentators and experts argued that the coverage of the problem largely amounted to scaremongering, it was only the safe passing of the main event horizon itself, the 1st of January 2000, that fully quelled public fears. Some experts who argued that scaremongering was occurring, such as Ross Anderson, professor of security engineering at the University of Cambridge Computer Laboratory, have since claimed that despite sending out hundreds of press releases about research results suggesting that the problem was not likely to be as big a problem as some had suggested, they were largely ignored by the media. Programming problem. The practice of using two-digit dates for convenience predates computers, but was never a problem until stored dates were used in calculations. The need for bit conservation. I'm one of the culprits who created this problem. I used to write those programs back in the 1960s and 1970s, and was proud of the fact that I was able to squeeze a few elements of space out of my program by not having to put a 19 before the year. Back then, it was very important. We used to spend a lot of time running through various mathematical exercises before we started to write our programs so that they could be very clearly delimited with respect to space and the use of capacity. It never entered our minds that those programs would have lasted for more than a few years. As a consequence, they are very poorly documented. If I were to go back and look at some of the programs I wrote 30 years ago, I would have one terribly difficult time working my way through step by step. Alan Greenspan, 1998. In the first half of the 20th century, well before the computer era, business data processing was done using unit record equipment and punched cards. Most commonly the 80-column variety employed by IBM, which dominated the industry. Many tricks were used to squeeze needed data into fixed-field 80-character records. Saving 2 digits for every date field was significant in this effort. In the 1960s, computer memory and mass storage were scarce and expensive. Early core memory cost $1 per bit. Popular commercial computers, such as the IBM 1401, shipped with as little as 2 kilobytes of memory. Programs often mimicked card processing techniques. Commercial programming languages of the time, such as COBOL and RPG, process numbers in the character representations. Over time, the punched cards were converted to magnetic tape and then disk files, but the structure of the data usually changed very little. Data was still input using punched cards until the mid-1970s. Machine architectures, programming languages and application designs were evolving rapidly. Neither managers nor programmers of that time expected their programs to remain in use for many decades. The realization that databases were a new type of program with different characteristics had not yet come. There were exceptions, of course. The first person known to publicly address this issue was Bob Beamer, who had noticed it in 1958 as a result of work on genealogical software. He spent the next 20 years trying to make programmers, IBM, the government of the United States and the ISO aware of the problem, with little result. This included the recommendation that the COBOL picture clause should be used to specify 4-digit years for dates. Despite magazine articles on the subject from 1970 onward, the The majority of programmers and managers only started recognizing Y2K as a looming problem in the mid-1990s, but even then, inertia and complacency caused it to be mostly unresolved until the last few years of the decade. In 1989, Eric Nagum was instrumental in ensuring that Internet Mail used 4-digit representations of years by including a strong recommendation to this effect in the Internet Host Requirements document RFC 1123. Saving space on stored dates persisted into the Unix era, with most systems representing dates to a single 32-bit word, typically representing dates as elapsed seconds from some fixed date. Resulting bugs from date programming. Storage of a combined date and time within a fixed binary field is often considered a solution, but the possibility for software to misinterpret dates remains because such date and time representations must be relative to some known origin. Rollover of such systems is still a problem but can happen at varying dates and can fail in various ways. For example, the Microsoft Excel spreadsheet program had a very elementary Y2K problem. Excel incorrectly set the year 1900 as a leap year for compatibility with Lotus 1, 2, 3. In addition, the years 2100, 2200, and so on, were regarded as leap years. This bug was fixed in later versions. But since the epoch of the Excel timestamp was set to the meaningless date of 0 January 1900 in previous versions, the year 1900 is still regarded as a leap year to maintain backward compatibility. In the C programming language, the standard library function to extract the year from a timestamp returns the year minus 1900. Many programs using functions from C, such as Perl and Java, two programming languages widely used in web development, incorrectly treated this value as the last two digits of the year. On the web, this was usually a harmless presentation bug, but it did cause many dynamically generated web pages to display the 1st of January 2000 as 1/19100, the 1st of January 100, or other variants, depending on the display format. JavaScript was changed due to the concerns of the Y2K bug, and the return value for years changed and thus differed between versions, from sometimes being a 4-digit representation and sometimes a 2-digit representation, forcing programmers to rewrite already working code to make sure web pages worked for all versions. Older applications written for the commonly used Unix source code control system failed to handle years that began with the digit 2. In the Windows 3.x file manager, dates displayed as 1/1, 19 to 0 for the 1st of January 2000. An update was available. Some software, such as Math Blaster Episode 1, In Search of Spot, which only treats years as 2-digit values instead of 4, will give a given year as 1900, 1901, as so on, depending on the last two digits of the present year. Date bugs similar to Y2K. The 4th of January 1975, this date overflowed the 12-bit field that had been used in the DEC System 10 operating systems. There were numerous problems and crashes related to this bug while an alternative format was developed. The 9th of September 1999, even before the 1st of January 2000 arrived, there were also some worries about the 9th of September 1999. Because this date could also be written in the numeric format the 9th of September 99, it could have conflicted with the date value 9999, frequently used to specify an unknown date. It was thus possible that database programs might act on the records containing unknown dates on that day. Data entry operators commonly entered 9999 into required fields for an unknown future date, in order to process computer forms using CICS software. Somewhat similar to this is the end-of-file code 9999, used in older programming languages. While fears arose that some programs might unexpectedly terminate on that date, the bug was more likely to confuse computer operators than machines. Leap year's main article. Zeller's congruence. Mostly, a year is a leap year if it is evenly divisible by 4. A year divisible by 100, however, is not a leap year on the Gregorian calendar unless it is also divisible by 400. For example, 1600 was a leap year, but 1700, 1800 and 1900 were not. Some programs may have relied on the oversimplified rule that a year divisible by 4 is a leap year. This method works fine for the year 2000, and will not become a problem until 2100, when older legacy programs will likely have long since been replaced. Other programs contained incorrect leap year logic, assuming for instance that no year divisible by 100 could be a leap year. An assessment of this leap year problem, including a number of real-life code fragments, appeared in 1998. For information on why century years are treated differently, see Gregorian calendar. Year 2010 problems. Some systems had problems once the year rolled over to 2010. This was dubbed by some in the media as the Y2K plus 10, or Y201K problem. The main source of problems was confusion between hexadecimal number encoding and binary-coded decimal encodings of numbers. Both hexadecimal and BCD encode the numbers chapters 0 to 9 as 0 by 0 minus 0 by 9. But BCD encodes the number 10 as 0 by 10, whereas hexadecimal encodes the number 10 as 0x0a 0 by 10. Interpreted as a hexadecimal encoding represents the number 16. For example, because the SMS protocol uses BCD for dates, some mobile phone software incorrectly reported dates of SMSes as 2016 instead of 2010. Windows Mobile is the first software reported to have been affected by this glitch. In some cases, WM6 changes the date of any incoming SMS message sent after the 1st of January 2010 from the year 2010 to 2016. Other systems affected include GFT-POS terminals, and the PlayStation 3. The most important occurrences of such a glitch was in Germany, where upwards of 20 million bank cards became unusable, and with Citibank Belgium, whose Digipass customer identification chips failed. Year 2038 problem. The original Unix time data type stores a date and time as a signed long integer representing the number of seconds since 1 January 1970. During and after 2038, this number will exceed 231-1, the largest number representable by a signed long integer on 32-bit systems, causing the year 2038 problem. As a long integer in 64-bit systems uses 64 bits, the problem does not exist on 64-bit systems that use the LP64 model. Programming solutions. Several very different approaches were used to solve the year 2000 problem in legacy systems. 3 of them follow. Date expansion. 2-digit years were expanded to include the century in programs, files, and databases. This was considered the purest solution, resulting in unambiguous dates that are permanent and easy to maintain. However, this method was costly, requiring massive testing and conversion efforts, and usually affecting entire systems. Date repartitioning in legacy databases whose size could not be economically changed. 6-digit year, month, day codes were converted to 3-digit years and 3-digit days. Only input and output instructions for the date fields had to be modified, but most other date operations and whole record operations required no change. This delays the eventual rollover problem to the end of the year 2899. Windowing 2-digit years were retained, and programs determined the century value only when needed for particular functions, such as date comparisons and calculations. This technique, which required installing small patches of code into programs, was simpler to test and implement than date expansion, thus much less costly. While not a permanent solution, windowing fixes were usually designed to work for several decades. This was thought acceptable, as older legacy systems tend to eventually get replaced by newer technology. Documented errors. Before 2000, on the 28th of December 1999, 10,000 card swipe machines issued by HSBC and manufactured by Racal stopped processing credit and debit card transactions. The stores relied on paper transactions until the machines started working again on the 1st of January. On the 1st of January 2000, when the 1st of January 2000 arrived, there were problems generally regarded as minor. Consequences did not always result precisely at midnight. Some programs were not active at that moment and would only show up when they were invoked. Not all problems recorded were directly linked to Y2K programming in a causality. Minor technological glitches occur on a regular basis. Some caused erroneous results, some caused machines to stop working, some caused date errors, and two caused malfunctions. Reported problems include: in Sheffield, United Kingdom, incorrect Down syndrome test results were sent to 154 pregnant women and 2 abortions were carried out as a direct result of a Y2K bug. 4 babies with Down syndrome were also born to mothers who had been told they were in the low-risk group. In Ishikawa, Japan, radiation monitoring equipment failed at midnight. However, officials stated there was no risk to the public. In Onagawa, Japan, an alarm sounded at a nuclear power plant at 2 minutes after midnight. In Japan, at 2 minutes past midnight, Osaka Media Port, a telecommunications carrier, found errors in the date management part of the company's network. The problem was fixed by 2:43 and no services were disrupted. In Japan, NTT Mobile Communications Network, Japan's largest cellular operator, reported on the 1st of January 2000 that some models of mobile telephones were deleting new messages received, rather than the older messages, as the memory filled up. In Australia, bus ticket validation machines in 2 states failed to operate. In the United States, 150 slot machines at racetracks in Delaware stopped working. In the United States, the U.S. Naval Observatory, which runs the master clock that keeps the country's official time, gave the date on its website as the 1st of January 19100. In France, the National Weather Forecasting Service, Météo France, said a Y2K bug made the date on a web page show a map with Saturday's weather forecast as 01/01/19100. This also occurred on other websites, including at.net. At the time, a general-purpose portal site primarily for AT&T WorldNet customers in the United States. On the 31st of December 2000 or the 1st of January 2001, some software did not correctly recognize 2000 as a leap year, and so worked on the basis of the year having 365 days. On the last day of 2000, these systems exhibited various errors. These were generally minor, apart from reports of some Norwegian trains that were delayed until their clocks were put back by a month.